This video is in response to Jack's latest video, which is linked below. I am reading this off of a script that I just wrote, so it is going to be fairly boring, and it's going to sound like I'm reading it off a script because that's exactly what I'm doing. So let's get started. For those of you just tuning in, here's a very brief summary on events leading up to now. In early 2024, I reviewed Jack's V1 battery for the Toyota Prius. In that review, I discussed several safety concerns, primarily that the V1 design lacked a per-cell battery management system, hence it couldn't detect when LFP cells were outside their safe operating area. I filmed this video prior to any of Jack's customers publicly disclosing that their NexPower packs had experienced thermal events. After I posted this video, one of Jack's customers publicly disclosed that they had experienced a thermal event while driving their NexPower-equipped Prius. A cell in this customer's pack melted down due to Jack's V1 design lacking per-cell supervisory control. Instead of having supervisory control, Jack relies on the Prius's OEM computer, which was designed to monitor nickel metal hydride cells. Due to differences in cell chemistry, nickel metal hydride systems don't require per-cell supervisory control. Instead, you can group several cells together in a string and then safely monitor only the voltage of that entire substack. This is not the case for lithium or sodium. Safety standards dictate that you must monitor each cell individually. The primary reason nickel metal hydride cells require less oversight is that nickel metal hydride's safe operating range includes the region where the battery voltage rapidly changes as the cell approaches empty or full. Therefore, with nickel metal hydride, it's safe to measure voltage every dozen cells or so, which is what the Prius does. For example, it's easy to measure a sudden 500 millivolt change when one cell in a string of 12 cells approaches empty. The Prius's built-in electronics have no problem measuring this voltage change, even though it's only measuring voltage once every 12 cells. But what happens when we replace the nickel metal hydride cells with lithium or sodium? Unlike nickel metal hydride, these cell chemistries don't have a sudden voltage change within their safe operating area. To be clear, they both do have a sudden voltage change as they approach empty or full, but unlike nickel metal hydride, these extrema lie outside the cell's safe operating area. Therefore, since the OEM nickel metal hydride computers are no longer able to safely measure the sudden voltage change, an originally nickel metal hydride equipped car that is now equipped with any of Jack's products loses the ability to limit assist and/or region while the cells are guaranteed to still be in their safe operating region. In other words, by the time the OEM computer detects a failing cell, that cell is already well outside of its safe operating area. A compounding factor is that both lithium and sodium cells are considerably more energy dense than nickel metal hydride and are much more susceptible to thermal runaway. Certainly, sodium is safer than lithium in this regard, but industry best practices still dictate, that's page 1 of 8. Industry best practices still dictate that sodium battery management systems to monitor individual cells in the stack. Jack's products do not provide this safety mechanism, which is my primary concern with his products. And if you look here on his PCB, you can see they do not provide per cell supervisory control. They do provide per cell discharging to a fixed voltage, but this does not allow or guarantee even that the cells will remain below that voltage, or if they do greatly exceed that voltage and go outside of their safe operating area, that we can alert the car. That's not guaranteed. Jack mentions in his video that the OEM computer will detect it because there's a 1.2 volt change, and again, I'm already getting off script here, so let's get back on. If you have any doubts about this safety concern, I have a challenge. Show me a lithium or sodium battery designed by a reputable company that doesn't monitor each individual voltage in the stack. If this were acceptable, car manufacturers would ditch BMS hardware altogether. BMS hardware is expensive. You have to run traces and wires to every cell. Why would you have that if you didn't need it? So going back to the first customer that publicly disclosed the thermal event. During my analysis, I determined that Jack had designed a signal soother product. That's this product here. That made the above issue even worse. The signal soother was specifically and solely designed to double the voltage at which the OEM computers would detect a cell failure. For example, if the system previously disabled the pack at 1.2 volts, then with the signal soother installed, you now had to get to 2.4 volts before the same disable criteria was met. You can watch my previous video on the signal soother for a complete breakdown of why that is. In other words, rather than fix Jack's poorly designed V1 and V2 hardware, Jack instead designed the signal soother to mask those shortcomings. In addition to the above safety issues, Jack's signal soother allowed high voltage to persist on the HVDC terminals even when the service disconnect plug was removed. This posed a safety hazard to service personnel. This was foreshadowing for at least the initial V3 prototypes wherein the service disconnect is completely bypassed. That's this here. I've lost my place. Wherein the service disconnect is completely bypassed. Removing the plug in these prototypes does nothing. The pack remains energized and unfused. Even though Jack added this functionality to later prototypes, the fact that Jack considered it safe to entirely bypass the HVDC safety fuse and the service disconnect and thought that this was appropriate because it allowed him to ship prototypes sooner is just beyond words. Particularly because he didn't notify and tell his prototype testers that that was in fact happening. That is a critical error in logic and reasoning. So here we are coming up on the official V3 NexPower product launch, and once again I have concerns. Summarizing my previous videos, my primary safety issue is that the V3 product reuses the V1 product's lacking circuitry. Here's the V3 product. There's the V1 product in quintuplicate. I don't actually have the 7 I would need to fully do this, but this is essentially the same here. In Jack's response, he holds up a V1 and V3 PCB side by side, implying that these are not the same, that they're different. I agree these circuit boards look very different to the untrained eye. However, the basic circuitry that insufficiently monitors each cell is functionally identical on V1 and V3. The primary visual difference is that each V1 PCB monitors 5 cells, 1, 2, 3, 4, 5, whereas each V3 PCB monitors 35 cells. I'm not going to count those, but that's 5 times 7. So this is my rendition of a V1 PCB that's adapted to look like a V3 PCB. These are functionally identical. And what do I mean by functionally identical? This is the circuit, or a version of the circuit on the board. This is the exact same circuit here with these 5 parts or whatever. 1, 2, 3, 4 parts now. I think we had more before. Oh yeah, we have some on the back. Of course, we have the resistors on the back. So before the resistors were on the front, and there was, well, that's my board. I've taped it together using one of my boards. So there's nothing on the back of Jack's PCB. Everything was on the front. Now we have it on the front and the back. So we have mechanically changed that. I addressed that previously. But we have 1, 2, 3, 4, and then effectively 5, because this is just 4 parts in parallel parts. So 1, 2, 3, 4, 5 parts. That's essentially the exact circuit. Now this one is 33 ohms, but this is the circuit, and it's duplicated 35 times on this board, and it's duplicated 5 times on each of these boards. Otherwise, these circuits are functionally identical. The last remaining thing here, I'll notice that when Jack held these side by side, implying they were different, he didn't actually talk about why they were different. There is a difference here. You can see, oh wow, we have different connectors here. These connectors are basically identical to those connectors. These are literally just because Jack got rid of the OEM BMS leads that would attach to the outside of every blade and has replaced it with this. It's the same thing we had before, except now it's here and routes out this way, whereas before we were reusing the OEM harness. So that is a mechanical and wire routing difference, but again, functionally, the schematic is identical to what it is or was before. The V1 and the V3 are functionally identical. There is no difference in what they are doing, except that the voltage set point is different because we're using a different chemistry. So again, both of these boards can only do one thing. At a fixed, unchangeable, unmeasurable voltage to the outside observer, each individual cell can be turned on and is turned on at any point in time when the cell gets above some voltage X. And then when it drops below that voltage X, it turns off. Both of these products do exactly that and nothing else. Nothing else. In Jack's latest video, he states that his PCB is designed to operate more than 10 years. And while that may be true, my concern is the actual cell lifetime, not the circuit board. Pro tip, you probably should add an acrylic conformal coating to your PCB if you want to overcome the oxidation issues you mentioned are so prevalent in the Prius. My Honda BMS product already does this, and my BMS product for Toyota will certainly have that as well. That will keep the oxidation down. So that Jack then spends several minutes attacking my product specifically. I feel like I've already responded to most of Jack's claims in my previous videos. So again, this is my product here. The only additional response I have is that the Toyota Prius product I'm designing is much smaller than my existing Honda Insight product, and also it won't have fans because the OEM Toyota's cooling system is quite a bit different than Honda's. And again, I've addressed the fans in my previous video. I don't see a reason to do it again. If Jack wants to discuss shortcomings in my products, I invite him to do so in a separate discussion. My focus right now is on safety issues in products he has manufactured, not mine. And of course, he hasn't actually noted any safety issues in my products. And if he wants to evaluate my products, let me know, Jack. I'll send you one. You can have it for free. I've offered several times now to pay for yours. I'll send you mine for free if you want it. I'm not even sure you know where to begin there, but that's conjecture, so. Rather than continue to defend my product, I'll point out that my hardware design is essentially unchanged since 2021 September when I ordered the Rev-C PCB. The only hardware changes I've made since then were due to COVID-related part shortages. My non-customer inflicted RMI rate is well below 1%. So during this time period, the same time period, 2021 September to now, you've iterated from V1.x, not sure how many revisions there, to V2, to V2.5, V2.8, and now V3. Also, your existing designs have a 30% RMA rate that I'm aware of. So why are you iterating your product so much if it's so well designed? What makes you think your V3 is going to solve all your previous issues, particularly since you're reusing your V1 circuitry essentially unchanged? Certainly you're not putting all your eggs in the same because it's sodium basket. If so, your customers are going to be disappointed when the same failures occur down the road. Note, I already observed a failure in the process of occurring in the pack that I looked at with that disconnected wire. We will discuss that more later. At 3:48 in your latest video, you state that the key to the battery system is battery, not circuit board. This logic is fundamentally flawed and shows your engineering team's inexperience. This is equivalent to saying you don't need to wear a seatbelt as long as you don't crash. In your own words, you told someone privately on your team that you don't see the value in having all the extra BMS hardware because it keeps your business simple. That's a decision that hasn't fared well with your existing products, so I find it incomprehensible that you would think you could keep using the insufficient V1 circuitry on your V3 product and think that it would work this time around simply because you switched to a sodium cell. That speaks volumes, and I'm sure we'll revisit the fallout down the road. Jack then spends several minutes responding to my mechanical concerns. I feel like I've already responded to most of his points in my previous video, particularly regarding the glue or thermal paste issue. Whether or not the adhesive you're applying is intended for use as a thermal paste, it is not achieving that goal as used in your product, hence why I'm simply calling it glue. It is an adhesive product, so let's call it what it is serving a function as, which is to glue things together rather than to dissipate heat. There's nowhere for it to dissipate heat. I did want to focus more on the cavities at the bottom of each module, so I've taken all the cells out so we can inspect the prototype design. Again, this is a prototype, but this is the hardware I have in front of me now. This is what I can review. So let's look at the mechanical support members. We have 3 posts in total. The bottom cells have 1 post in the middle each, here, there, here, there, here. So we have 7 total, 1 per cell. Nothing on the sides here, which is a very odd choice, particularly because this is a very flexible member here. So any support this provides is going to be flexible. So that's interesting. Presumably this sits on a metal structure here that would keep this supported, and then the same issue would apply here as well. I don't believe that the OEM nickel metal hydride mechanical enclosure actually has the rails that you were using here. If it does, let me know. Again, the Prius is not my area of expertise, but batteries and electronics are. So the bottom cell has this 1 post, and then each middle cell has 1 post on the outermost end. So each cell, there's 2 cells across in the middle, and we have 1 support here and 1 support there. No support here. I don't completely understand why. No support there either, just you have a middle support there. In addition, there are a few rubber pads on a few cells. So 1, 2, 3, 4 rubber pads. There are no other pads. If this is a structural element, I'm confused why it isn't on all of the cells. It would probably be because it affects airflow. Regardless, this is too flexible to provide the mechanical support we would need. So even on these lower cells, the mechanical support is inadequate, and let's look at why. Here I've drawn a cross-sectional view of that pack, so that would be this standing up. This drawing is like that. So we're going to do this here. You can see the supports. This is that support, and then this and that are the supports on the end here. And what you have is you have a cell on the bottom that's teetering like a seesaw, and you have, so you can see that it can actually bump up here or bump up there. This is actually a little bit made worse because there's actually a bus bar that runs along the bottom of these cells. I didn't draw the one on this side. And this bus bar has a heat shrink applied over it, but it actually stops slightly short of the bend. So we actually have this bend radius pushing as well. Now, on half of the cells, that's not going to matter because this is going to be connecting to the negative outer jacket, the outer cylindrical wall. On the other half, though, this would be a potential difference. So that is certainly something worth noting. The cells are outside, so I can't show you that right now. Taking these out of this pack was not something I was going to do inside because it brings you from very little mechanical support to no mechanical support, and I don't want those cells to short out. I suspect that if I fully discharge those cells, I mean, of course, if I fully discharge those cells, I'd be able to remove them and play around with them without risking shorting them out. So even on these lower cells, the mechanical support is inadequate because it can move up and down here. There's nothing to prevent these cells from vibrating back and forth, and thus causing rubbing wear between modules. So you'd have rubbing wear here, rubbing wear there, and then of course the rubbing wear I mentioned here and there and here and there. As this pack deforms, whichever member is pushed down, so one of these pairs is grounded, so either the outer pair is grounded or this bottom one is grounded, depending on how this installs in the pack. It doesn't change the outcome though, is that these members are not strong enough to keep the weight of this pack from flexing in and out as you run over. We'll talk about that more later. So in particular though, you'll note that all of the upper cells lack any mechanical support whatsoever from the case enclosure. So the cells that are supported, first of all, only have 1 support, and second of all, it's only these lower cells. So it's weird to me that we don't have more ribs here and here to provide this lower guy much more support, and then again, I don't understand why we don't have a ribs here and there as well to provide mid support at least on these cells. And then of course the 3D printed or hopefully injection molded weave honeycomb between them would provide cell support for those upper structures. I've already talked about that. So In short, my previous position on the mechanicals has not changed. I recommend adding a plastic mechanical separator to both support all the cells and also to provide better safety isolation between cells to prevent wear rubbing. You have twice now proposed that my proposal is identical to the tape solution you're using now. It worries me that you continue to think these are equivalent. Show me another cylindrical traction battery that uses anything close to your design. I don't even know how to respond to Jack's statement at 5 minutes and 5 seconds that the cells have to be freaking flexible. This is nonsensical and irrelevant to the safety issue I'm pointing out, namely that a safety issue exists between your cells where they can physically touch each other. As it pertains to this safety issue, flexibility is a moot point if you have properly designed mechanicals that both support all cells and also keep them physically isolated from each other. Of course, for high reliability, you'd want to reduce flexibility as much as possible, but that's not the safety issue I've identified. Flexibility has nothing to do with the root cause of this issue, although it could contribute to the wear that would lead to it. Note that if we had had this conversation months ago in private, it would probably be less painful for you to change the design. But here we are butting heads publicly on the eve of your product release. I understand the defensiveness in your position, but I think it's entirely self-inflicted. Once again, I propose that you consider my feedback before deploying thousands of these suspect designs in the field. Take it or leave it. Next up, Jack spent several minutes discussing the merits behind soldering cells. It doesn't matter that your soldering is done by professionals. This misses the point entirely. Even if your soldering expert is using equipment that can heat and reflow in less than 6 seconds, this is still not an accepted industry practice because the amount of energy it takes to heat the cell and copper tab so that everything melts and reflows properly and forms a good connection results in considerable heat at the end of each cell. This is bad for the internal cell chemistry. At 10 minutes and 40 seconds, Jack mentions that soldering costs more than any other method. I agree this is true, and so my counter is, why are you soldering cells? At 10 minutes and 48 seconds, Jack states that he solders cells to get the lower internal resistance, and that only soldering can do that to bond two metals together. This is factually incorrect, as both mechanical fastening and tab welding create lower resistance connections, which are also more reliable and cheaper too. I'll note that both of my existing products have 10 times lower internal resistance than the V3 sodium prototype that I evaluated. One of my products uses ultrasonically welded tabs between cells, whereas the other one uses mechanical fasteners, and yet they both have vastly lower resistance, even in the bus bars. One benefit to using mechanical fasteners is that you can make your bus bars as thick as you want, so they have lower resistance. Whereas with soldering, the thickness is limited to how much heat you can dump into the copper bus bar before the cell is damaged. Copper is an excellent conductor of heat. The thicker you make it, the faster it's going to wick away the heat and the harder it's going to be to solder, and that's why you have to use thinner bus bars, which increases your resistance. At a certain thickness, you simply cannot solder the tab on without damaging the cell. Both ultrasonic and laser tab welding are also limited by tab thickness, but the amount of energy that heats the cell is considerably lower in both of these methods, hence you can use thicker materials up to the adhesion limits of ultrasonic and laser tab welding. If your process is as dynamic as you say it is, why wouldn't you tell your manufacturer to switch over to a cheaper, stronger, lower resistance, faster to install tab attachment process? It doesn't make sense that you would continue to solder these cells given these facts. I'm amazed that you continue to stand behind soldering. I have never seen this in any traction battery in any vehicle I've looked at. Show me a reputable automotive manufacturer that solders cells together in their traction batteries. Show me your CATL datasheet that allows cell soldering, and I will drop this point. This is not even my main point. I have a few other points to discuss unrelated to the safety issues that I just identified and discussed in more detail. At 30 seconds, Jack discusses why he can't send me a product. I've asked to review his products in several different contexts, so I'd like to discuss each one individually. When Team Jack initially approached me last year, they were trying to fix their lacking battery management system. This is by their own admission. As is typical when consulting, I asked for hardware to evaluate along with existing schematics. Without boring you with the details, I've already done that, so if you want them, you can go back and look. I was essentially told that the designs were top secret, so I couldn't see them. That's in jest. And also that I couldn't evaluate the existing hardware on similar grounds. This is a very odd thing to tell someone you're considering consulting with. Note that at this point in time, we were still on good terms. Specifically, I hadn't even spoken with Jack yet. I was still working with his Team Jack member, the anonymous person. So there really wasn't any reason to deny me access to this hardware, particularly because they wanted me to fix their lacking design. Because of this, at my own expense, I procured an LFP NexPower battery from a third party and was aghast when I looked inside. You can see my reaction in the first NexPower video I posted back in 2024 February. So that's the context behind why I asked for your 1.x and or 2.x hardware. That's what was released at that time. For the V3 hardware in my latest asks, note that I'm not asking for the production hardware. It's very clear if you go back and rewatch that. But rather I'm asking for a later version of your prototype. I asked for this new hardware specifically because you mentioned that my 2024 May prototype was very old. 3 months, 2.5 months old. Hence the reason why it had an internally bypassed service disconnect. That's this point here that you made. The first response you made to me ever, actually, on the forums, back when we could do that. I wanted this later prototype so I could evaluate your claims. I never asked for production hardware, but to be honest, it shocks me that you're still iterating a design this close to release. You said mid-August, that's like 2 weeks from now. How are you supposed to internally validate the final product before shipping it to your customers if it still doesn't exist this close to release? Are your first paying customers your guinea pigs? This is atypical in a properly engineered products development cycle. You would have your final hardware, or you're very close to final hardware. You know, you have to like move one trace because you failed EMC or radiated missions. Yeah. At 1 minute and 20 seconds, Jack also proposes that he can't send me anything because I keep trying to sue him. I have not sued Jack, and I have not attempted to sue Jack. I have no intent to sue Jack. However, I did send Jack a cease and desist because he was privately slandering my professional reputation to several people in this small industry. A few of those people know me personally and reached out with written evidence. In addition, a few people I don't know and had never spoken with provided additional evidence regarding statements that Jack made regarding my professional capabilities. My cease and desist focused solely on those actions and has nothing to do with Jack's existing products. Meaning the demands I laid out in my cease and desist are easy. All Jack has to do is stop spreading falsehoods regarding my professional reputation. That's all I asked for. This is a small shared field, and attacking my professional reputation could be catastrophic to my career. Next point. Jack proposes at both 7 minutes and 25 seconds and 8 minutes and 52 seconds that the separated wire I showed in my initial V3 teardown was sabotage just to put on a show. I refute this claim entirely. Why would I risk my professional reputation by inducing yet another defect into your already poorly designed product? Also, did you ask your manufacturing team if they ever spliced wires together on these prototypes? And if so, does that give you pause that maybe they messed it up? I wonder if other prototype packs have the same issue around this era, you know, the other packs made around this time frame. Be interesting if some of the other prototype customers would check that to see if they have cells that are spliced on the end caps, you know, this side or that side. Whether or not I cut this wire and then soldered on a different colored wire to sabotage your product, I didn't. To be very clear, I didn't. My safety critique remains unchanged. With your V3 design, this PCB, if a voltage sense wire becomes disconnected, This 100% guarantees that the two cells immediately adjacent to said wire will no longer discharge those cells. Since the other cells will still discharge, this will cause these two cells to overcharge over time. This is guaranteed based on this architecture. And your system presently has no way to detect this until the cells get so overcharged that the OEM Prius computers detect a massive voltage deviation, at which point the two sodium cells are almost certainly damaged due to overcharging. Why don't you want to include the proper VMS circuitry to detect this defect long before it becomes problematic? This design is completely free. It's open source. And if you don't want to use the Arduino, don't use the Arduino. Take the 2560, slap it down on this board. I mean, that's probably what I'm going to do on the Prius version because I don't need the mechanical standoff. It's free. Next point. At 12 minutes and 2 seconds, Jack says, if you don't like my product, don't review it, don't buy it. Jack fails to understand why I'm reviewing his product. It's unsafe. It's unsafe because it's poorly designed and remains poorly designed even after numerous revisions. It simply blows my mind that the V3 hardware here reuses the V1 circuitry in its entirety, and Jack knows that it's inadequate. And yes, it's better than the V2.8 circuit board I reviewed. That was the worst one. But jumping back to a known defective V1 design is insanity. And it's unsafe. And that's why I'm posting these reviews, to prevent potential customers from using unsafe hardware. So yes, my recommendation is the same as part of Jack's response. Don't buy his products. If Jack ever designs a product that is safe, I will post a review stating so, and until then I feel compelled to point out safety defects in dangerous products. It's absurd to think that I should keep my mouth shut and watch as other people buy defective products. I'm reviewing your products to prevent your customers from wasting their money on unsafe products. My penultimate point, before we get to the crescendo, is Jack calling me an online troll in his latest video. Calling me a troll is a classic ad hominem attack. Trolling is the act of provoking others with inflammatory, irrelevant, and offensive comments, typically with a lack of sincerity. A troll's intent is to disrupt valid conversation, typically as a way to seek amusement or satisfaction from seeing others react negatively. I'm doing none of these things. In fact, you never reacted to any of my previous critiques prior to like a few days ago, going on months now. That's not why I was doing this. I am not trolling you for several reasons. I have intent and domain-specific expertise, which I use to highlight safety issues with your products. I don't post these safety concerns for my own enjoyment, but rather my overwhelming purpose is to protect our community members from unsafe products. Your product is unsafe. Finally, let's discuss Jack beating a NexPower V3 module to death. We're on the last page. With a rubber hammer. I certainly was not expecting that, and admit that it looks great on film. An untrained eye is likely to walk away from your video thinking, wow, this is safe because Jack beat it with a hammer. But let's dig a little deeper to see what precisely you accomplish by destroying these cells in this pseudo test. First off, beating the pack for a few dozen seconds is far from equivalent to the vibration-based wear that accumulates over millions of stress cycles. Why don't you send your pack to a shock and vibe lab and see if it can survive ISO 16750's test gauntlet? For example, random vibration tests based on IEC 6008-2-64 and sinusoidal vibration tests, blah, blah, blah. These are things where you run a test at like 5 Gs for an hour in the X and then the Y and then the Z dimensions. That would be a more accurate test than just beating your pack with a hammer. But on this note, I have to ask, was that pack charged? If so, you have big cojones performing that rage-induced experiment indoors. What would have happened if it short-circuited? Or was the point of that test to show that no matter what you did, a short circuit couldn't happen? If so, I would like to propose a test where instead of beating on an object like a primate, you actually induce a short between connected cells in the pack and then see how it responds. My guess is that the bus bars would probably melt off. I think that would be the most favorable outcome, to be honest, is that the solder gets so hot that the tabs just fall off. Hopefully they don't fall to the cells below and short them out. Probably they would. There's nothing to retain them in place. On the other hand, if the pack was discharged, then you haven't proven anything. Beating a pack with fully discharged NMC cells would produce the same results. Nothing would happen because there's no stored energy left to produce any appreciable response. And speaking of energy, let's talk about how much total energy is inside a fully charged V3 NexPower pack. That's 2.3 kilowatt hours from my measurement, or thereabouts, which is equivalent to around 8 megajoules of energy, which is about the same energy that's inside 8 sticks of dynamite. So if the pack was fully charged, you were very lucky nothing happened. And of course, if the pack was discharged, then all you did was vent your self-induced anger onto your poorly designed product. So was that pack charged or discharged? Okay, so that's my response to Jack's latest video. At this point, I think we've both stated our various claims. It's probably time to let the product speak for itself in customers' cars. Certainly, many people will be happy with his V3 design. But that doesn't mean it's a safe product for the several reasons I've mentioned previously. As always, thanks for watching.